Good morning, welcome. Last time we have looked at stability. So it's coming from ODEs actually to see whether small changes in the initial condition, for example, in our case in the numerics it would be at any point in the computation, can amplify, get very large so that the difference in the solution gets so large that we cannot use the solution any longer. And the requirement was then that we want that the numerical solution has to be bounded. And we found out we can do that by applying the ODE method to the test equation, which is a very simple scalar equation. And then we can see from that whether that will be amplified, the solution will be amplified, then it is unstable, or it will be bounded, then it is stable. Let's continue on that. We looked at Euler's method. Now we want to look also at the Runge-Kutta methods, and we start with Heun's method. So let's check stability. For Heun's method. Just a reminder, what was Heun's method? You have done that for exercise 2. In the first step, we compute the right-hand side of the ODE at the old time level, Tn, and with the approximation we have at that time level, Yn. By the way, if you do the programming, it is advantageous actually to use the function that you have already programmed to use ODE 45. Then you have just one function evaluation. So you initialize your initial condition as a vector. Vector, in our case, it was the position, x, y, and the initial velocity, uv. You have a vector, then you have a y1. And then you can start already using that from the first step on. Just one function call, that's all. Then you have it. And the second, again, just one function call. Later called it func. And then you do it at Tn plus Hn, that is the step size from Tn to Tn plus 1. And then we evaluate then the function at essentially the Euler step, Yn plus Hn k1. So that is what you would do if you would do just Euler's method. Start from the old solution at time level n and add the step size times the slope at the old time level, which in our case would be k1. So then we have two slopes, and then Heun does it in such a way that the solution at the new time level is computed by taking the old one and then adding the step size Hn and the average of the two slopes k1 and k2. So that is what you did for exercise 2. Now we want to check the stability by applying the Heun's method to the test equation. So we apply then this method, Heun's method, to the test equation. And the test equation, that was, we had the number for that earlier, that was 3. Y prime is lambda y, and lambda is a complex number and it is constant. And the link to the ODE that we are solving is by considering that lambda would be the Jacobian of the f with respect to y. If we have a scalar ODE. If we have a system, then the lambda would be one of the eigenvalues of the Jacobian. We have an initial condition, y of 0 is 1, simply 1. So that is dealt with test equation. And now we apply the method, or we use the method to solve this test equation. And what is then our f? So if in that case the f that we have done, that we have to use then in Heun's method, What is the f in our case? It is simply lambda y, the constant times y. So we have an extremely simple right-hand side of the ODE. And then we assume, assume we use now for the derivation, because that makes things a little easier, just h for hn. We have a constant step size, but that we also often do when we actually do the computations. But we are free to choose it. For example, using the step size control to change the time step from one time level to the other. So then we compute now the first slope for this ODE. So that is f of Tn Yn. F of Tn Yn. So that gives lambda Yn, right? Lambda Yn. The K2 is f of Tn plus Hn. We have no time dependence in the test equation. And then we have here Yn plus Hk1. And that means we have lambda times this, that is Yn plus Hk1. So our f is lambda y, that means lambda times this. And then we can use what the Kn was, and we can then insert that. So that was, as we saw before, lambda Yn. And then we can see that we can simplify that. We can actually factorize Yn. And we get then lambda, here we take the 1 plus, we take it the other way around, lambda h, and then we have Yn. So lambda is out here, and here we factorize the Yn, so we get 1 plus h lambda, lambda h. So that would be then K2. Then the Yn plus 1 is equal to the Yn plus, now we do the average, h times the average of the slopes, K1 plus K2, then we simply insert what we have. So that is Yn plus h half, then we have lambda Yn for K1, and we have here lambda 1 plus lambda h Yn. So then, so that is here. Now we summarize what we get in the end, and we can see we can factorize Yn directly. So then we get, from this we get a 1 plus, here we have a lambda Yn, and here we have a lambda Yn. So we get that 2 times, and with this 2, it goes away, so we get, together, we get a lambda h. Remember, we factorize the Yn. And then what is left is h half, and here we have a, that is lambda h, this gives a lambda h half, and this gives a lambda h half. Lambda h squared divided by 2, so we get then lambda h squared divided by 2, and we had factorized the Yn. So from that we can then see the amplification factor. Of Heun's method. And that is, as we argued, the ratio of the solution to the test equation, or we can also argue, we can, if we apply that recursively, this formula, we can see then that this will be the factor that we multiply each time when we go to the next time step. So then we get that, we call it directly g of lambda h, And we say that is the yn plus 1, the solution at the new time level, divided by the solution at the old time level. And we see in our case that will give then 1 plus lambda h plus lambda h squared half. And then we saw last time the stability condition for that to be bounded. Remember the recursive formula was that this is to the power n. If we want to compute the time level n, then it means that we have to take this amplification factor to the power n. So the condition was that this amplification factor in absolute value has to be smaller or equal 1. So that was the stability condition. And that gives us the boundedness of the solution for the test equation. That was that the amplification factor of lambda h has to be smaller or equal than 1. So then we get the condition in our case for that. So that means in our case then that we get that in our case we have the condition then that the 1 plus lambda h plus lambda h squared divided by 2, that has to be smaller or equal than 1. So that is our stability condition. So when we choose h, because lambda is given, in our case it would be then by the Jacobian of the ODE, then that gives us then a condition how large we can choose h, the time step. And like in Euler's method, we can also draw a picture of that and look at the real and imaginary part of the lambda h and look for the domain out of which we can choose the lambda h such that this condition is fulfilled. That is called the stability domain. So the stability condition over there is equivalent to saying that lambda h is inside the stability domain, which is then defined by all complex numbers for which 1 plus z plus z squared half in absolute value is smaller than equal than 1. So then we can try to find that. And say a brute force way would be that we simply choose z in the domain that we expect. It would be, say, around 0 and to the left of that. For the real part, say, like Heun, in the imaginary part somewhere, we would choose simply a couple of numbers, compute that, and then let MATLAB draw the contour line where it is 1. Then we would get the boundary of the stability domain. What we would get will be the following. We have here the real part of lambda h, the imaginary part of lambda h. We will get the following. We assume that we have -1, -2. Let's see, it's not drawn to scale because I need to go a little bit up here. 1, and we have to go up around here to around 1.73 imaginary unit. Here, down here, we have to go approximately to minus 1.73 I. And what we get is roughly an ellipse, not quite, but almost an ellipse. So we get something of this. So that is our stability domain of Heun's method. So it has 0, so the origin is here, it is just inside. There the stability, we have 1. You can easily see that. If we have z equal to 0, we get just 1. So it's inside the domain. And then we get up here, and that is at -1 to approximately 1.73 on imaginary units, and also down here to minus of that. And here we cross the real axis at -2, just as Heun's method. Remember, Heun's method was just a circle. So this is now not drawn to scale, 1, 1, but Heun's method was just a circle. So we win a little bit in this part here, which is then stable for Heun's method, but not for Euler's method. Regarding the real axis, we don't win anything. So when we have a lambda that is real, the stability for Heun's method and for Euler's method will be the same. So that is what we get. What we can also note, what we have here, or what we have our stability or amplification factor here, that is actually an approximation. If you look at it, this looks like we would continue lambda h to the power 3 divided by 6. It would be an approximation to the exponential of lambda h, which would be the exact solution to go from 1, say from 0 time level to the next time level. So that is actually a third order approximation of that. So just make that as a remark. Note the 14, our amplification vector, is the third order accurate approximation of the exact solution of the test equation 3 that would be at t equal to h. So that is then, if we start from 0. So then we would have y of h, that is then our t in that case. For the exact solution, it would be e to the lambda t, and if t is h, we get lambda h. And that is, as we just started to argue, simply if we do the Taylor expansion of that, we get lambda h squared and half plus lambda h to the power 3 divided by 6, and higher order terms. And then we see what we do with Heun's method. We just take the steps, the terms up to in second order. So we get a third order approximation. That is the highest order error term. And that is actually corresponding to the local truncation error. So then what we have here is the amplification factor. And what we have here is actually minus, but would be this order h to the power 3, corresponding to the local truncation error, actually the minus. So if we write that explicitly, then it would correspond to the local truncation error. That is at step 1. In our case, we have a convention the other way around, so it would be different. So that is just a side remark, but it's just as we expect. Of course, this would then be the step from the time level 0 to the first time level. Then we see that Heun's method is giving us a third order approximation for the local truncation error. And then we know the global error will be one order lower, second order. That is what we argued before. Okay, so then we see the stability, and we see if we have a real lambda, then we do not win regarding stability. We win, of course, regarding accuracy, because this method is second order accurate, Heun's method, while Euler's method is only first order accurate. Now let us also do this analysis, but we do it a little shorter, for the classical Graham-Cutter method. Of course, all these methods that we discuss now are used in CFD. Then we have to have an understanding of what are their properties, and also particularly regarding stability. So then we want now to discuss the stability of the classical fourth order Graham-Cutter method, which we call RK4. And we apply now the RK4 to the test equation f of ty is equal to lambda y as before, and get, you can do that as an exercise, g of lambda h is equal to, and here we get a couple of terms more. So that was what we got for Heun's method, but now we can expect that this will be a more accurate approximation of the exact solution e to the lambda h. And in fact we get here, the next term is lambda h to the power 3 divided by 6, as it should be, and then lambda h to the power 4 divided by 24. So 3 faculty, 4 faculty, and that's it. So that is the amplification factor that we get. So, and we see from that that this is equal to the exponential e to the lambda h plus the fifth order error. So because we have now a local truncation error that is of fifth order, that gives a global error of fourth order. So the stability condition now is that this g of lambda h for Graham-Cutter 4 has to be smaller or equal than 1. The condition RK4 is then in this form. See the absolute value of the amplification factor that we have here, that we can write in the following form, that we write it as a sum, infinity from L from 0 to 4. Then we have lambda h to the power L divided by L faculty, that an absolute value, so that is now short notation of this, these first 5 terms of the Taylor expansion of e to the lambda h, that is representing the amplification factor of RK4. That has to be smaller or equal than 1. So then we can also look for the stability domain for this. So that is then we can just here continue the argument here. More here. So now we have to represent then it in this form. If we do that, so we say it is to be the domain for now we replace lambda h essentially by z. So then we have here z to the power 3 divided by 6 plus z to the power 4 divided by 24. Absolute value that has be smaller or equal than 1. we can do the similar thing as we did for Heun's method, but I still have to tell you the more clever way to do it. So we could again choose a couple of z in the complex plane, compute the values of the absolute value of this polynomial in z, and then plot the contour line where that is equal to 1 to get the boundary of the stability domain. Another way, or a more clever way to do it, would be, we know that 0 again is in the stability domain. It's actually on where the stability, where we have this absolute value equal to 1. We could start here, give it a small delta y, and then assume that z has the form x plus iy. So we give the y, and then we get a nonlinear function for determining the z. We would put it then in here, and we would then find out where then the y here, where at this y location is the x, such that this absolute value of x plus iy with the y given is equal to 1. That is simple, a nonlinear equation. You can easily solve that by Newton's method. And when you have this point, you will find out it will be very almost on the imaginary axis. You can go on. So you can build up your boundary, and what you will find is something like this here. It's a kidney shape. It's symmetric. So it should here be symmetric. Good. And what you have here is still the origin, and we can actually compute the values where we cross the imaginary axis. It turns out that these values are exactly 2 square root of 2 times imaginary unit. That's here minus 2 times square root of 2 times imaginary unit. And the value that where we cross the real axis is minus 2 square root of 2. In this domain here, that is the stability domain of the RK4. So if we look at it a little bit, it should of course be symmetric with regard to the real axis. If we look at it, we see if lambda is real, then this will be important, 2 square root of 2. So remember, for Euler's method and Heun we had 2 here. And here we have just about 2.8 something. So we don't win very much here for doing the double work for then Heun, 4 functional evaluations instead of 2, 4 times the work compared to Euler's method, 4 functional evaluations, Euler's method only 1. We don't win very much. So that is like that. But we win something very important on the imaginary axis. Now suddenly we have a complete interval from minus 2 square root of 2 to plus 2 square root of 2 on the imaginary axis inside the stability domain. That means we can now allow for imaginary lambda. We will see when we do the PDE discretization for hyperbolic problems, we use central discretization there, then we need that. We can get a stable method with RK4, but not with Heun, not with explicit Euler's method. So that is the big advantage of this method regarding stability. So the RK4 stable for lambda imaginary that is if lambda is equal to yi, and I is now the imaginary unit, used already there. If the absolute value then of now our lambda is yi, and the absolute value then is y h. We take lambda h. So that has then to be here, and that means it has to be smaller than 2 square root of 2. So then we can get it stable. There are a couple of other arc cutter methods around in CFD, and we also like one that is third order. There's only 3 functional evaluations, and it keeps a certain property for conservation laws, which we might discuss later. But there are a bunch of them around. So we just look now here at the most important ones for us. So far, stability, we'll come back to that later when we discuss implicit methods, because all methods that we have been discussing now were explicit methods. In explicit methods, we saw that we just need to evaluate the function with some values that we know or that we just have computed. For example, in Heun's method, we do the function evaluation for k1 with the old time value yn, for k2 with the value that we would have computed with Heun's method. So we have this, we can compute it directly. With implicit methods, you need to approximate the slope at the new time level that we do not know already. That is something that we will discuss probably today. But before doing that, I would like to continue on what Radar told you on Tuesday about stiff ODEs. Because they pose certain problems when we want to solve them numerically. So the name is coming from structural mechanics. If you have a spring that is difficult to pull or to press, so then that is called stiff. In ODEs, there are not so clear, not such a clear definition. There are actually definitions of stiffness, and I would like to give you some of them by Michael Heath. That is an author who has written a book which I recommend if you really want to have some basics of numerics. Then this is called Scientific Computing. An introductory survey that is of 2002 in McGraw-Hill. So he gives a couple of definitions. The physical definition is the following. Physically, a stiff ODE describes a process with highly disparate width timescales. In the example that we are going to do as exercise 3, you will get an example from chemistry, chemical reactions. You might have reactions that go very fast, immediately almost, and some that take very long time. So then you have by the time of the reaction to take place, different time scales. And if they are very different, then you have a stiff problem. We'll see also in a minute some simpler examples of that. We can also characterize by stiffness by looking at the solution of a stiff ODE. Solution of a stiff ODE contains rapidly changing varying transients, so that are intermediate solutions. So when something is changing, but is slowly varying otherwise. So these rapid changes or these rapid transients are only in certain, maybe just small time intervals. And in the example from the stabilizing flame that radar showed on Tuesday, it was only at some location that something happened. That is also typical. And then Heath also gave the mathematical characterization for systems. So, mathematically, a stable ODE system. So that is now means that we look now at a vector y. Say y prime is f of ty. That means that y and f are vectors. Now I assume that they are m vectors. So that means y and f have m components. So a stable ODE system is stiff if its Jacobian matrix that we already have seen to characterize stability, J is the derivative of f of ty with respect to y. So that gives it a matrix then when we do that. If that has eigenvalues that differ greatly in magnitude. And that means test that we have the following condition in that case, that the minimum of the absolute value of these eigenvalues of the Jacobian, therefore we have now m, so we have m eigenvalues then, and the absolute value, the minimum of the modulus of those has to be much, much smaller than the maximum. So that is then the condition. And where we have assumed here that the lambda L, where L is from 1 to m, are the eigenvalues of J. So that means we have we have a stable ODE, then these eigenvalues have all negative real part. But here we are saying that the minimum is much, much smaller than the maximum. So we have very disparate scales, and they actually translate to the time scales. So that is something that we can check by computing the Jacobian and its eigenvalues, and then we can check that.
Swapman?
Yes?
What if some of the eigenvalues are complex and some are real?
That is not a problem.
How can you compare them in size?
It's a complex number. You take the real part squared plus the imaginary part squared and take the square root.
Oh, okay.
That's the absolute value. No problem. You have actually different occasions for that. When we have it real, it is usually related to some damping. Because remember, the solution for the scalar problem is e to the lambda t. And if lambda is negative, real, e to something very large negative times t is damped very quickly. But still we have to take that into account with the stability. Although it vanishes very quickly, but it's still present. If lambda is complex, then we have something that is oscillating. Because then we have e to the I lambda, or part of it at least, and that is cosine I plus I sine 1. So that can give then, and if that is large, we have a large frequency. So that is both our problems. So therefore this is it's one way to do it.
Yeah.
So you can characterize these different situations. Large damping compared to very small damping when it's real, and very little, low frequency, imaginary part is low, and very large, then you have high frequency. Small oscillation, very large oscillations. So it characterizes these extremes. And regarding the scalar ODEs, it makes things much nicer and it's easier. Scalar ODE, we have simply that lambda is j. So then the Jacobian itself is already the eigenvalue. So then we don't need to do any work on that. So let me just finish this characterization before we go into examples after the break by noting the characterization by Ernst Heyer. And here have Wanner. And also that, they are authors of the book. I'll show you something of that later. It's called Solving ODEs 2. In the first volume, Sivat Nurset is second author, Solving ODEs 1. And this is on stiff and differential algebraic problems, so actually on what we are discussing here. And that is from the second printing, or the second edition, that is from 2002. And they say the following, and that is a numerical, so I call it a numerical, they give a numerical definition of stiffness. I quote them from actually the first sentence after they have introduced, say, the concept of stiffness from different languages actually. Stiff equations are problems for which explicit methods don't work. So that is a very simple definition. So that is what Radar said the other day. If ODE 45 doesn't work, if that takes forever, or you get strange results with that, then it's probably a stiff problem. But you can analyze that before you use it. Okay, before we go into the break, I have a very important thing that I forgot last week. That is the reference group. We need a reference group, and particularly for this course and also at this stage, because it's a new course, so we need your feedback. So it would be nice if we had representatives, say, of all the study programs that are represented, but it's also nice if we have different people from the same study program. So who is ready to be in the reference group? Very good. Very good. Very good. Okay. You were from Energy and Environmental Science.
Yeah.
Marine. Very good. And Machine. Okay. 3 big groups represented. Very good. So if others want to join, please do that. So those who said they are ready to do, please contact me during the break, then we can discuss when we meet first. I've also discussed with Radar, but I would first want to hear with you when you are available. Okay, so then we take now 15 minutes break.